Now we're in a position to go into more of the details of the Snapdragon 805 SoC that we introduced at the beginning of the course. If you recall, here's how the chip is generally organized. We have a lot of specialized processors. We have a controller for connecting to memory. And then we have the crate general purpose CPUs. And they all work in parallel and coordinate with each other in order to perform a complex task such as playing a game. Now let's look at the details of the quad-core crate processor. Now this is a pipeline diagram that flows from top to bottom rather than left to right as we've seen in most of our diagrams. The high performance techniques that we've studied in the course that are embedded in the crate CPU include pipelining, superscalar execution, out-of-order execution, SIMD processing, caches, and multi-core. We're going to talk about caches and multi-core a little bit later. Let's focus first on the pipeline design. At the beginning we have instruction fetch and decode, which comprises 3 pipeline stages. Now the crate pipeline can fetch and decode 3 instructions at a time. Also in these 3 stages is a branch predictor that predicts the outcome as well as the target of a branch instruction. Decoded instructions are placed into an issue queue where they wait before they get sent to the different pipelines. After the issue queue, we've got a lot of different pipelines. There's a lot of parallelism going on in this processor. Let's first focus on the left-hand side, which is devoted to processing integer instructions. From the issue queue, 4 instructions can go to 4 different places in parallel. The first pipeline stage in each of those 4 is called expand. Now we talked about in the course how some complex instruction sets will create simpler instructions from a complex instruction. Well, it turns out that the crate CPU does this even with ARM instructions. So for instance, some ARM instructions combine a shift operation with an add in one instruction. And if there's a complex shift, something more than say shifting 1, 2, or 3, then that will be separated into 2 instructions, a shift instruction and an add instruction. And these are called micro operations, where we break a complex instruction into smaller internal within the hardware, simpler instructions. The next stage, the rack stage, is where we access the register file. After reading the registers, instructions are placed into reservation stations. Now these are like the issue queues that we talked about for out-of-order execution, where instructions and their associated source operands are placed in the queue where they wait for values from dependent instructions to be bypassed. Now you notice that there's a line between the in-order part of the pipeline and the out-of-order part. Up until the reservation stations, instructions are handled in the order of the program. But just as we talked about with out-of-order execution, instructions can come out of the register file and go to the execution units out of their original program order. Notice that we have 7 separate integer pipelines. So we can have up to 7 instructions sent from the reservation stations in parallel in a single clock cycle. Now let's talk about the function of those 7 execution pipelines for processing integer instructions. The Y and Z pipelines handle simple integer instructions such as addition and subtraction. The X pipeline can handle more complex integer instructions, while the M pipeline is dedicated to integer multiplies. The LD and ST pipelines are dedicated to load and store instructions, including the calculation of the address. Finally, there's the B pipeline, which handles branch instructions. So depending on the mix of instructions, we can have 7 integer instructions flowing through their associated pipelines at the same time. So that's how the crate can exploit a lot of instruction level parallelism within integer instructions. Now let's move on to discussing Venom, which stands for vector numerics. That's shown here on the right-hand side of the diagram. The first stage of the Venom pipeline grabs up to 4 instructions from the issue queue. Those are then placed in the VU queue, which is the Venom Unit Instruction queue, where instructions wait until their source operands become available. Notice now that's where the out-of-order execution part of the Venom pipeline starts. Instructions issue from the VU queue into 3 different pipelines, and each of these handles 128-bit wide operands. The VX pipeline handles arithmetic operations. Now this includes single instruction multiple data or SIMD integer operations on 128 bits of data. So for instance, if we were doing operations on 16 bits, you can do 8 of those in parallel with one SIMD instruction. The VL and the VS pipelines are for handling load and store instructions. Again, those are also dealing with 128-bit wide data. The expand stage handles micro-op expansion, similar to what we saw with the integer pipeline. Now an example is the ARM table lookup instruction, which requires a lot of operands to be fetched, more than we typically want to have the ability to fetch from the register file. So that's broken up into multiple simpler instructions so that we don't complicate the register file too much. After that, we have the evaluate stage, and this determines hazards between different instructions. And those are resolved in the resolve stage. In the rack stage, we read source operands from the Venom register file. And that's followed by a number of additional VX stages for performing computation. There's also a Perm Block, and this is for doing permutations of data, which are part of the ARM instruction set architecture. Now if we go back to look at the entire picture, we see that we have up to 10 instructions that can be executed in parallel. 7 on the integer side and 3 on the Venom side. Now that's a lot of support for exploiting instruction level parallelism within a single program. Now that we've seen the details of the crate CPU, let's move on to the multi-core design and the cache hierarchy. Now within each of the crate CPUs, you see that we have 4 different caches. We have a level 0 cache on both the instruction and data side, and that's also connected to a level 1 cache for both instructions and data. Now the idea here of a level 0 cache is to have a very small, simple cache that can be accessed very quickly. Now both of these are only 4 kilobytes in size, which is pretty small for a cache. And they're also direct mapped. Now if you remember, we talked about direct map caches are very, very quick to access. And that's their advantage, and that's why they're used here. So for example, to get an instruction from the L0 instruction cache, it only takes a single clock cycle. Whereas larger, more associative caches may take multiple clock cycles to access. The L0 data cache requires 3 cycles to access, and both of these caches have a 64-byte block size. Now if an instruction is not found in the L0 cache, it might be found in the L1 cache. Now this is bigger and more associative, so it's slower. Each of the L1 caches is 16 kilobytes in size, 4 times the size of the L0, and they're also 4-way set associative, so they take longer to access. So for instance, the L1 instruction cache requires 4 cycles compared to the 1 for L0. However, because they're bigger, then the hit rate is going to be higher. So we're more likely to find something in the L1I cache than the L0 cache. The L1 data cache is the same size as the L1 instruction cache, but it requires 6 cycles to access. So long as we find the instructions or data in our L0 caches, then our pipeline can progress without delay. If not, then we look in the L1 cache and we pay an additional small delay. Now behind the L1 caches is a shared L2 cache. Now this may be 1 megabyte in size, much larger than the L0 and L1 caches. It also has a larger block size, 128 bytes, and it's more associative. It's 8-way set associative. Now it's organized this way so that we'll have a high hit rate, so that we don't have to go off to the slower main memory if we miss in the L2 cache, and we don't have to do that too often. Now what's interesting about the L2 cache is it operates asynchronously with respect to the L0 and L1 caches. It runs off its own independent clock. Now it takes about 10 cycles typically, 10 processor cycles to access the L2 cache. But that's going to depend on how fast we run the L1 caches. And each of those is individually controlled. And the reason that we do this individual control is for power consumption reasons. So here's a diagram of 3 crate CPUs that each have their own clock and their own voltage. Now we talked with some of our guests about this means for saving power consumption. where we can change the clock and we can change the voltage when the task that we're running doesn't demand that we have the highest frequency. So we can set the frequency of each of these CPUs to the speed that's needed to carry out their given task. Now, in order to have this independent operation of each of the CPUs, we allow the L2 to run off its own clock and its own voltage. So now when we have an L1 cache miss, the number of cycles to access the L2 will depend on the speed that the processor is running at. And again, we arrange the chip in this way in order to minimize the amount of energy that we use in our SoC so that our batteries will last longer.